In 1980, building a computer chip required working on a microscopic scale. One engineering team attempted a superchip so massive it required industrial liquid cooling and heavy metal containment to survive its own operation. The architect behind this machine was Gene Amdahl, the designer who had built IBM's mainframe empire. Investors handed him $250 million to execute his vision. Manufacturing tools could only expose a 1/4 inch square of silicon at a time. Wafers were printed with dozens of these squares and diced apart, isolating defects. If a stray particle ruined one chip, you threw it away and kept the rest. Amdahl abandoned dicing to pursue wafer scale integration. His new company, Trilogy Systems, would use a massive, unbroken 2.5-inch slab of silicon as a single monolithic superchip. By refusing to cut the silicon into isolated pieces, the project shifted into a statistical trap. A canvas that large guaranteed it would absorb fatal microscopic defects. In semiconductor manufacturing, everything revolves around yield, the ruthless economic metric measuring the percentage of working chips harvested from a single silicon boule. Mathematical models like Murphy's and Poisson's dictate that a silicon wafer is never a clean slate. It functions as a microscopic minefield. As you trace the small 1/4 inch boundaries, most survive, but a few inevitably encapsulate a stray particle of dust and die. Expanding the physical footprint to 2.5 inches forces the boundary over a massive area. The single chip swallows dozens of these fatal flaws simultaneously. Under these probability models, an uncut wafer of that size possesses a 0% survival rate. Trilogy had committed to a multi-front war against physics. The first battlefront was thermodynamic. To hit mainframe processing speeds, Amdahl chose power-hungry emitter-coupled logic, or ECL transistors, ignoring the slower, cooler CMOS alternatives. Packing millions of these ECL transistors onto an unbroken slab generated enough concentrated heat to turn the logic circuit into a localized thermal weapon. Standard aluminum heat sinks melted under this stress. To contain the temperature, engineers clamped the delicate silicon between thick, heavy industry molybdenum plates. They hermetically sealed this metal tomb and subjected the internal logic to violent cooling forces. Liquid fluorocarbon and compressed helium gas were pumped directly over the silicon surfaces to pull the heat away. This mechanical assembly happened inside a hyper-controlled, pristine environment, forcing human technicians to marry heavy industry with microscopic precision. The team built an active industrial containment facility for the sole purpose of keeping the logic gates from burning themselves alive. To survive the physical defects hiding on the wafer, Trilogy deployed a logic architecture known as triple modular redundancy. Every calculation was sent down 3 identical parallel circuits. If one lane encounters a physical defect, its pulse is destroyed. A central voter circuit observes the arriving data, ignores the broken lane, and passes the surviving signal forward, uninterrupted. Amdahl hard-coded this voting logic into hardware law, filing patents for a system that assumed structural failure was inevitable. But forcing 3 distinct physical copies of every circuit bloated the architecture. The redundancy logic tripled the physical real estate required on the silicon. By expanding the footprint to accommodate the safety logic, the chip swallowed even more of the microscopic minefield. The mathematical solution designed to bypass the defects guaranteed the chip would be struck by more of them. In the winter of 1982, an intense El Niño storm system hit the California coast. Heavy rains overwhelmed the drainage infrastructure and engulfed entire neighborhoods in the Santa Clara Valley. The floodwaters breached Trilogy's manufacturing facilities in Cupertino and Sunnyvale. The pressurized cleanrooms required to execute wafer scale integration were contaminated, grinding production to a halt. The $230 million Trilogy Superchip was dead, but the patents for the 1,200-pin copper-polyimide multi-chip module interconnects survived. Recontextualized, these schematics operated as a technological virus, waiting dormant for a new host. That host arrived in the form of Digital Equipment Corporation. DEC was a massive computing titan, and they licensed Trilogy's interconnects to solve their own logic bottlenecks. DEC integrated these complex components directly into their flagship mainframe project, the VAX 9000. But the tight thermal tolerances and manufacturing requirements of the Trilogy designs paralyzed DEC's assembly lines. The VAX 9000 was delayed, ultimately resulting in a $1 billion loss. The engineering decisions made inside Trilogy Systems survived on paper, traveling outward to infect and collapse an adjacent empire a decade later. Today, a company named Cerebras Systems is successfully manufacturing massive, unbroken slabs of silicon to power artificial intelligence. They achieved wafer scale integration, finally proving the conceptual framework drawn up in the 1980s. Gene Amdahl's original architecture wasn't flawed. He was simply 40 years too early, fighting a war against the material science of his own era.